Okay, so we're having more people joining, so I think it's good. Okay, shall we get started?
Sure.
Okay,
Yes. Yeah.
so yeah, welcome back to Agriforwards CDT Science Seminar Series once again. My name is Fumiya Ida. I'm a Deputy Director of the CDT project, and I'm very pleasure of having Dr. Iain Flint from Cheese Growers this time as a guest speaker of the seminar series. Just to give you a bit of announcement that the CDT project is now starting recruiting another cohort of master PhD students starting from October 2021 next year. So if you're interested, please spread the word and try to apply for this opportunity. So just give you a bit of an introduction to the Iain Flint and Cheese Growers. I have a very special feeling about Cheese Growers because this is the company I first time started our agricultural robotics project, and without Cheese Growers, we have not doing agricultural robotics project. So I'm very happy and excited to work with the Cheese Growers for last few years. And Iain has joined this Cheese Growers last year or two, and he's leading the technological innovation there. So Cheese Grower is doing a lot of impressive large-scale and reliable operations of vegetable supply and production. But also they're investing a lot of efforts and money to the innovation of technologies. And Iain is one of the technical lead in the Cheese Growers. So I'm very much looking forward to the current operations of Cheese Growers, as well as their perspective to the future development. So without further ado, I think I will just give floor to Iain, and I'm looking forward to your presentation today. I will just release my screen share, and I think you should be able to join with your screen.
There we go. Can you see my screen?
Yes, perfect.
Brilliant. Thanks very much. Thank you very much, Fumiya. Thank you for the invite to come speak today. I'll just make a brief correction to what you said, that I'm not actually Dr. Iain Flint. I think that'd be quite important for your audience. Before working for Cheese, I was a PhD student actually at the Cambridge Engineering, but I joined Cheese right towards the end of my PhD. So I've got a background in mechanical engineering, not actually in agriculture. So as of 2 years ago, I was new to the world of agriculture, but it's been an absolute pleasure to be involved with Cheese and carry on some of the really great work that was started about 3 years before I joined. So I will start today, here, let me just, there we go. I will start today by giving you a bit of an introduction to who we are at Cheese, who Cheese as a company is. And then I'll talk a little bit about this idea of farming 4.0. That's in my title, a bit of an analogy to Industry 4.0, which is, I think, a much better defined and understood term. I've seen farming 4.0 thrown around quite a lot, and digital agriculture, precision farming, those kind of terminology. And I wanted to talk a little bit about that idea and what it means to us as a company, and why we're motivated to get involved in this space. I'll then talk a little bit about the challenges that are facing our industry right now and why that's pushing us towards the kind of innovative work that your CDT is doing. And then we'll talk about a couple of the projects that we've run over the past 5 years and the impact that's had on us and where we're looking to go in the future. So a little bit about Cheese. We are a family-run company, established in 1952, so coming up to 70 years quite soon. We have about £500 million in turnover every year, of which we reinvest about 4% of that, as you can see here. And that comes from that family-run idea of investing for the future, thinking about the long term. We grow in 5 different locations across Europe and also Senegal in West Africa. Primarily, we grow in the UK. So you can see here we grow over around 6,500 hectares in the UK and a similar kind of area in Spain. And then smaller volumes we grow in the Czech Republic, Senegal, and Poland. We are a fully vertically integrated business comprised of many different companies under the G's group. So we have our own greenhouse in the UK, as well as greenhouses in Spain, where some of our crops begin their lives before they're transplanted into the field. We then have farming operations. We've got 17 different growers that are part of the cooperative that employs me in G's. We've got packing facilities for everything from onions and beetroots through to celery stick pack factories and so on. And then we've got our own sales and marketing companies. So from seed all the way to selling things off to all the major retailers in the UK and many in Europe, we cover most of that process. Rather than go into any more detail on this, I've got a video that we've made that I think says a lot more than I can do in 3 minutes. So we'll have a go at playing this and see if this can give you a good idea. I'll just ask Fumiya if you can interject if this video is too blocky to be showing properly. So we start here. You can see our seed nursery. So this is where many of our plants, our celery and our lettuce, begin their lives. You can see as seed blocks. They spend anywhere from 3 months to as little as 2 weeks before being sent out to the field to plant. Here you can see our planting rigs, putting the blocks into the ground, starting off their life, and boom, there we go. At the end of the life, they have lettuces ready for harvest on our harvest rigs. Moving on to our baby leaf operations, where you can see spinach being drilled in and now harvested. Again here, very different to lettuce. It's being harvested mechanically, less labor intensive, because it's quite a different product. So you can see the variation going from one lettuce product to another. It's a really different growing system. And here it is being packed into bags. We also grow radishes, which you can see here, again, harvested in an entirely different way, mechanically, and then sent through a wash line. This is a view of our celery operations, being planted in a similar way to our iceberg lettuce crops, and beautiful mature celery. And here you can see where this one is being processed into a higher value product sold in stick packs. As of 2012, we are also growing mushrooms in the UK. This is our state-of-the-art facility in Littleport, just north of Ely, where our head office is based. And you can see the only thing that we grow without sunlight. Here they are being packed into punnets, ready for the supermarket. We also grow beetroot, and you can see here they're being peeled, packaged, and then in quite an innovative process here, they're being steam cooked in the package before being then packed and palletized and sold. And I think the final one we have here is our, oh no, second last, this is our onion operation. Again, you can see different crop, different operation, different means of growing. And here it is being graded on the line at our facility, I believe in Ramsey, again, north of Ely. And I think final one here we have is spring onions. So you can see there a field full of beautiful spring onions ready for harvest. And again, very different harvesting process here, one of our most labor intensive. And yeah, we grow internationally, as I mentioned, in Spain. Here you can see some of our celery operations in the Aguilas Valley in southeastern Spain, and some of our tomato greenhouses, and our propagation greenhouse in Spain. So that's just a bit of a introduction into our different operations. I think without seeing kind of a video like that, those sorts of images, you don't really understand the scale of what 6,000 hectares in the UK means. So hopefully that was a useful introduction. So moving on to what's in the title of my talk, this idea of farming 4.0, and trying to put a definition to this, because I couldn't find quite a lot of material on this term, even though I've seen it pop up more and more, especially at conferences. So I see farming 4.0, precision farming, digital agriculture kind of being used interchangeably. And it's obviously, with farming 4.0, it's an analogy to industry 4.0, which was originally proposed by the German government as an idea for a fourth industrial revolution. And I understand that to be the incorporation of sensors, digital models, artificial intelligence to create smart systems of productions or smart factories. Farming 4.0 then is obviously the agricultural equivalent of that. It's bringing in internet-connected sensors and machinery into the farming environment to enable decision support systems and autonomous systems for growing more intelligently and in a more automated, more efficient way. What I absolutely couldn't find, though, looking anywhere, was a definition of what farming 3.0 was, or 2.0 or 1.0. So I'm going to have a go at defining that. So if we start looking at the much better defined industry versions, you've got industry version 1.0, which is of course the Industrial Revolution, things from the spinning jenny to the steam engine, the application of the mechanization of production, and the use of coal and steam to start increasing what an individual worker can achieve. That then being scaled up in this technological revolution, what you would call version 2.0, where access to fossil fuel power really scales up what we're able to achieve. We see steel and cement production exploding in this period, car production going up by, I think, a factor of 8 between 1860 and 1970. That then giving way to the digital revolution, version 3.0, where we're seeing a continued increase in energy consumption, but not a tremendous one like it was in the previous revolution. But the introduction of computers changes the way we manufacture things. It allows us to do things more intelligently. And we see the introduction of some automation, some the beginning of robotics coming into production. So then version 4.0 is then, as I understand it, an extension really of the digital revolution, where we're seeing artificial intelligence really starting to take off, because we're getting integrated circuits with over 1 billion transistors from, I think, 2010 onwards. We hit that threshold at that point. We see the concept of the Internet of Things appearing, and we're seeing digital twins being used in practice. As I understand it, Rolls-Royce have a digital twin of every engine that they sell, in order to maintain them while they're in service. That's to me, that's what Industry 4.0 looks like. And we're seeing, I think, robotics really starting to take off. The example in the fresh food sector that comes to my mind is Ocado's packing facility, where they have a combination of human and effectively robotic or automated packing robots doing logistic operations far more efficiently than you can do without them. It's also worth pointing out that there was a version 0.0 to industry before the Industrial Revolution, and that is cottage industry. It's people doing things by hand and relying on animal and wind and water power. I bring that up because if we look at the agricultural equivalent of this, there was a version 0.0 then of agriculture, and that is what is widely called the agricultural revolution. It's agriculture being discovered somewhere around 10,000 BCE. You quite often hear the Fertile Crescent in the Middle East being the origin of agriculture, but it's actually discovered in 5 or 6 different locations independently around the planet. If we're looking for an equivalent to the Industrial Revolution, the best thing I could find was the British Agricultural Revolution, which occurred from roughly 1700 until roughly 1900, where you see, again, mechanization becoming important. We're seeing a scientific approach to farming, things like crop rotation being developed in the East Anglia region, where most of our farms in the UK are, and you're seeing things like selective breeding coming in. Over this period, I believe the population in Britain tripled between the years of 1750 to 1850. And if you look at food production, that same tripling is about what occurred. That then gave way to the kind of industrial agriculture era, if we want to put a name on the second version, which is again fossil fuels, internal combustion, allowing us to access far more energy than we were ever able to use before, and having the machinery to allow that. Critical for farming was the development of processes to chemically produce fertilizers, so the Haber and Ostwald processes to go from methane and nitrogen gas to ammonia fertilizers, as well as irrigation systems such as the center pivot system, which was developed in the 1940s in the US, I believe. That then gives way to the Green Revolution, as it's called, which took place around 1960, where the development of high-yield varieties of wheat allowed us to massively increase the yields of cereal grains. and the development of synthetic fertilizers and pesticides allowed us to better control what we were doing in the field. And obviously, computers played a role at this time, just like it did in the digital revolution, but to a lesser extent than what you see in manufacturing. So what does farming 4.0 look like? Well, I'm hoping it looks a bit like what we see in that in the top right there, which is a little shot of VeggieBot, which Fumia alluded to in the beginning in his introduction, a project that the Bio-Inspired Robotics Lab has done with cheese growers. To me, it's the application, again, of digital twins, of artificial intelligence and automation to allow us to farm more intelligently. Just to put some numbers on this, if you look at wheat production in Britain in terms of the productivity per land area, so per hectare here, in 1700 we were producing 700 kilos, 0.7 tons of wheat for every hectare that was covered. Over the course of the first revolution, that tripled to 2 tons. In the next one, it doubled. And in the Green Revolution, again, almost a tripling in our production. So in the previous revolutions, we have been able to do far, far more with the land that we have available to us. It's up for debate whether that trend will continue in the future. It's leveled out in the last 20 years. We haven't really seen yields of cereal grains increasing. So there's a chance that we now have to be farming more intelligently. We're getting to the point where we're yielding close to what we can from the land, and we need to do things a bit more intelligently. These previous revolutions allowed us to farm at absolute massive scales and really minimize the amount of workforce we needed to grow the food that we need. I believe in 1850, 20-something% of the population in the UK was involved in agriculture, whereas if you look at it today, 1.5% of the UK population is involved in agriculture. So that's a bit of a history, and that's my proposal for how we think about farming 4.0 in terms of what's happened in the past. So if I move on to some of the challenges facing my industry today, this kind of speaks for agriculture generally, but specifically for horticulture or for fresh produce, for the salad vegetables that we grow. We face issues with finding people to work in our industry. That's becoming more difficult. We find issues with the ways that we've been farming historically, with the legacy of the Green Revolution, of the pesticides and fungicides we use becoming more restricted, and in some cases seeing resistance causing problems. We're seeing the environmental impact of the way we farmed historically, and that's requiring us to make changes. And we're seeing the impact of climate change. It depends who you talk to on their perspective of this, but many people in the agricultural sector will tell you that they are noticing changes to the weather. They are saying the weather feels more extreme, it feels warmer. So that's a kind of anecdotal evidence of climate change. If you wanted to trust people who spend their entire working lives outdoors, they will tell you the weather is getting more extreme. It's a bit of a challenge for me in our business to define what more extreme means, but nonetheless, we need to adapt the way we grow to the possibility that the climate is changing, not just getting warmer, but becoming a different system. And finally, there is pressure for ever cheaper food, more affordable food, which, as you can imagine, directly goes against some of our other challenges. So just to put numbers on that last point, here is for iceberg lettuce, a bit of market data to give you some context. In green, you can see the price of an iceberg lettuce kind of averaged across supermarkets. So you can see in 2013, the average price for an iceberg lettuce, if you went into Tesco or Sainsbury's or M&S, Aldi, you would see about 80 pence being charged. And with the introduction of Aldi and Lidl coming into the market in 2014, you see this quite tremendous drop off in the price, with a corresponding jump in the amount of consumption of those products. But if you look at the line in blue here, you can see the total value of this product for the sector decreasing. So it's a good story for consumers. They were getting a more affordable product, a significantly more affordable product, but a difficult story for supermarkets and a difficult story for us as the producers to enable, run a business in those conditions. As a point of interest, this point in the timeline here is when we began the 2 projects that I'm going to discuss in a bit more detail today. So you can see there's a direct correlation between these price pressures and innovation, which is a good thing in my mind. Labor is also obviously a challenge for us. You've probably seen quite a lot about that in the news this year with COVID-19 restrictions. But before that, we had issues with labor availability driven by general market trends, but also exacerbated by Brexit. In 2015, we had 750 people on our waiting list to come do seasonal work at G's. By 2017, we had nobody on our waiting list anymore. It's the combination of Britain leaving the EU and the weakening of the pound meant that many of the people that come to work for us seasonally from Eastern Europe no longer find the UK an attractive proposition. So there's a big challenge for us in simply sourcing the labor to come work for G's. So a combination of automation and upskilling a labor force in the fields will quite significantly help that pressure. In terms of chemistry, one example that came to mind was chlorpyrifan, which is a herbicide that we previously used, but that was banned by the EU last year. It was no longer you're no longer allowed to purchase it from the beginning of this year, and as of last Thursday, all stocks had to be used up for growers in the UK. And because horticulture is a much smaller industry by revenue or by scale than, say, the arable sector, it's difficult for companies to justify developing replacement products that can help us control some of the weeds without damaging the crops we grow. Alternatively, hand weeding to replace these chemical methods will be extremely expensive and labor intensive, and directly goes against the labor issues that we're already facing. So we need solutions for handling weeds. If only somebody could design a weeding robot, something like that. Talking about environmental impact, I don't know if anybody has watched the new David Attenborough, A Life on Our Planet series yet. I can't recommend it highly enough, but he starts that series off with Chernobyl as an example of what can happen when we don't take care of our environment, that we can make places uninhabitable. Another example came to my mind when I watched that, and that's the Dust Bowl in the US, where my family are from, the Midwest. So over the course of the 1930s, there was an 8-year period of droughts that exacerbated existing problems with the way farmers in that area were managing the land. They didn't understand the ecology of the Great Plains particularly well, so they were doing wheat and corn production, plowing, combine harvesting, and not irrigating the land. And the combination of the extreme weather that occurred during that period, those extreme droughts, and that really extractive agricultural process led to, in some places, 75% of the topsoil being permanently lost, and land prices decreasing by as much as 30% in those regions. And still to this day, many of these areas are permanently damaged. The ecology permanently changed in this area, and certain crops can't be grown there anymore. So my grandparents grew up as children during this period, and this is what we could be facing if we don't do a better job managing our land. If we see topsoil erosion, we could see a lot of our fertile land being degraded in this way again. Probably not to this extreme extent, but we have to do something about it. And finally, there is currently the impact of some of the environmental damage that is happening to the planet of more extreme weather. We're seeing more extreme rain. We're seeing, I believe, 9 out of the 10 hottest years on the planet in the last decade. Last autumn, we had very heavy rains that you may have heard about, significantly reducing yields of cereal crops this summer. And interestingly, just this spring, we had the sunniest spring by, I think, a factor by 20% we've ever had in the UK. So I think a lot of people just assumed that they were working from home and they were spending more time outside, going for walks perhaps, but it was legitimately the sunniest spring we've ever had in the UK. Now, these are each on their own anecdotes, but they kind of seem to add up over the years. There's a suggestion that we are dealing with more extreme weather, which means we need to think about growing in a different way. We need to be flexible because what we've done in the past may not suffice in the future. So in order to handle these challenges, what do we have to do, or what do we have to be? To handle labor shortages, we need to be thinking about being more automated. To handle these restrictions on the chemistry we can use, we need to be more targeted in our approach. To handle the environmental impact, we need to lower our impact. We need to be thinking about what happens to the places where we're farming. To handle climate change, we need to be more resilient, maybe flexible is another way of putting that. And finally, and summing up effectively everything here, if we are going to continue on this trend of trying to make things more affordable, providing more value to people in this challenging environment, we need to be more efficient. That's really what it comes down to. And that, in summary, is why we are interested in this concept of farming 4.0. We've got these pressures on our industry, and we think the introduction of robotics and automation will really help us make the changes that we need to handle these kinds of challenges. So I will finish my talk today by talking about a couple of projects that we've done over the last 5 years. And just before I start into those, I'll talk a little bit about our production process. So as you may have seen from the video, for what we call whole head crops, so that's our lettuces and our celery, which makes up, I think, a little around just under half of what we grow, I believe. It's a two-stage process, so it begins in a greenhouse. So if something is sown in our greenhouses for the beginning of the season, we might put that into a greenhouse in the beginning of December and plant it out in February. So it's taking 90 days or as short as 15 days in the middle of the season when it's much warmer. Once it's planted, it then spends some time in the field, what we would call its grow days. So again, things planted in the spring taking 90, maybe 100 days to come ready, whereas things planted in the summer having a much shorter growth cycle. The numbers you see here are specifically for iceberg lettuce. And in that production process, we have, like any manufacturing process, losses. Some of what we sow in the greenhouse won't germinate. Some of what we plant into the field won't establish. Some of what we bring ready to harvest won't be of a high enough quality that we can actually sell it to our customers. It might suffer from pest damage, from disease damage, or other quality issues, or it might not fit the specification that's asked for by our customers, and that's where this unharvested loss that you see there comes from. And finally, we're in the fresh produce sector. A lot of what we grow can't be held in the field for a long time once it reaches maturity. And once we do harvest it, it has a very short shelf life. It can last for around 5 to 7 days on the shelf, as you'll see from your Best Buy days if you go into the supermarket. The effect of that is that if we have crop available to sell in a given week, we need to sell that week. If we have 3 million lettuces available one week and demand for only 2 million, we're not going to be able to sell that remaining million. And the sad impact of that is that we will then end up plowing that crop back into the field, which does provide green manure to the field, so it is being reused. It's not wasted necessarily, but all the effort and resources that went into producing that crop were in effect wasted. The converse of that is if we have demand that we can't meet with our own crop for a mismatch of planning, then we will bring in crop from other regions, which obviously increases food miles and cost to us as a business. So all three of these, the traded volume and these three losses, the unestablishment, the unharvested volume, and the plow in here are, from an engineering perspective, inefficiencies to the system. And that's where we should target our attention. And that's what we've done with two projects that I've been involved in. The first one is our growth modeling project, which we call IceCam, standing for Iceberg Crop Adaptive Model. We found that if you give things a brand name in a business, they get more mileage. People give them more attention. I don't need to tell anybody here that plants need light and the right temperature to grow, but it's been established, I believe, at least since the 80s, that for some crops, a set number of accumulated degree days, so temperature over time, is a very good proxy for maturity. So you say that iceberg lettuce requires 700 degree days to come to maturity as a sort of rule of thumb. That works to a greater or lesser extent, depending on the crop. But we started with that concept working with Microsoft Research in 2015 to create a model based on the response of photosynthesis to temperature and light, to understand how our crops are responding to changing weather. We have grow days in mind for how long it will take our crops to come to maturity based on the time of year. But this modeling effort allows us to understand what happens when we see temperature and light that is very different from what's typical in that time of year, and what that means for the availability that we'll get, whether we'll be short or long in terms of crop that's available in any given week. And with enough foresight, we're able to do something about that. We're able to arrange promotions with retailers, or we're able to change our growing program in the future and manage our crop to help mitigate the impact of that. As of 2019, compared with 2013, we had seen a total 6% improvement in our yield in that period, which isn't just due to this modeling effort, but this has been a significant part of what allowed us to make that improvement. That means we're using less land and less resources, or fewer resources, to grow the same amount of crop, meeting some of those challenges that I was talking about earlier. This year we started introducing applications that we've made in-house using Microsoft Power Apps to kind of help facilitate this process. And we're hoping from next year forward, we'll be able to extend our growth modeling work to not just forecast when our crop will be ready for harvest, but also characteristics such as the distribution of things like the size of the lettuce heads or the weight, which will allow us to better manage our harvest. What are the ingredients that go into a growth model like this? We take about 10,000 hand measurements of our crop every season, and we've been doing that since 2015. So we've got a really good database now of how our crop grows, what the life cycle of an iceberg or a little gem lettuce looks like. We have all of our planting and harvest data going back 6 years. We got sales forecasts feeding into this. We've got weather from our own stations, as well as forecasts in the short term, and we're experimenting with longer term seasonal forecasts to understand how to use that information. And finally, this model is implemented in a combination of model training that I do in Python, and for simplicity, we run the actual model itself just through Excel calculation tables and create outputs for our growers in Excel. But that will change over the coming years as better technology becomes available. The second project I'll talk about is our remote sensing project that, again, we've given it a name. We call it Agri-Eye, our eye in the sky agriculturally. This project began as a knowledge transfer partnership with Cranfield University in 2015. By 2017, they had helped us develop our own in-house counting algorithm using imagery captured from light aircraft. With some manual processing, we were able to segment the imagery into plant and soil layers, and then identify where each plant was and make an estimate of its leaf area. In the following 2 years, we kind of developed KPIs and outputs from that information that allowed our growers to use it. It sounds simple, but just knowing the number of plants that are alive in the field makes a huge difference. We assume that 95% of what comes out of our greenhouse and is sent to the field for planting will establish for our lettuce that we grow. However, if poor establishment occurs for usually some sort of weather-related issue, that could be as low as 80%. So if we don't know that we have that low establishment, and you can't always tell from walking the field, we might be expecting to have far more crop available than we actually do, and that will be a surprise for us at harvest. With this information, it's not a surprise. We know early on in the crop life cycle that we have this issue coming up, and we can do something about it. Last year, Hummingbird Technologies developed a deep learning method with a masked region convolutional neural network based on ground truth image from our fields that really improved the accuracy of this counting. And you can see an excerpt from the paper that they published, I think, last month, detailing how they did that. And this season, between the UK and Spain, where we're running this project, we've now flown 4,700 hectares of our crops, so a significant fraction of where we grow. Our ambitions for next season are to look at variable rate application of nitrogen based on this imagery. From some trials, we've seen that applying nitrogen only to plants that need it can significantly reduce some of the variation in size, which for us is directly linked to our eventual yield because if we have variation in the size of our populations, that means that some plants will be too small to harvest when the majority of the population is ready for harvest, and some plants might be over mature at that point and have quality issues associated with them. So a little bit of what this information actually looks like. Here is one of our planting maps that as of this year we've been recording digitally. So you can see in blue there the boundaries of each seed variety planted in this field. Each of these batches is somewhere between maybe 1 to 3 hectares in size. So this total field here is quite a large one. This is about probably a 25 hectare field full of iceberg lettuce. So there's close to maybe 1.5 to 2 million plants in this field. In each of these little red squares here, you can see, if we zoom in, what the output of this counting algorithm looks like. So you can see a bit of the scale of what's going on here. So the outputs we get now tell us in square centimeters what the ground area cover is, or leaf area index, from above, what area each plant is covering in terms of leaf area. And if you look, I don't know if you can see my cursor here, but you can see there's an example of a plant that didn't establish for some reason. And you can see that there's a variation in size here. And if you look at the population distribution here, you can see there's usually a coefficient of variance of around 0.25 to 0.3 of this ground area cover. So this information lets us know if we're seeing a larger coefficient of variance at this stage, we're looking at a batch that is for some reason more variable than history, which tells us we're likely to get a lower yield out of that one. If we see one that's more uniform, we're expecting to get a better yield out of it. Obviously, looking at every individual lettuce like this in one image would not give you any real information. So grouping them into 2 by 2 meter squares here and showing the average leaf area gives you an idea of where smaller and larger regions in the field are. So this is the field grouped into 3 different regions, where the white region is smaller, going to the pale green, and then the darker green being the largest plants. I put this here to point out that even experienced growers walking the field can't get a full picture from the ground of what's going on in the field. That if they began a transect of the field, they would assume that batch 363 was large and 365 was small. If they moved to the right and started their walk from here, they would probably come to the opposite conclusion, seeing that batch 363 was small and 365 was large. You really need to get this kind of eye from the sky at the scale that we're growing in order to understand the variation that's going on. So hopefully that gives you a bit of a picture of the kind of information that we've been getting from remote sensing. So finally, I'll just put those 2 projects into context and back on this production diagram where they fit in. So our growth modeling work allows us to target these inefficiencies. It allows us to better manage our growing program so that we can reduce the amount of crop that we're unable to sell because we don't have the demand, and making sure that we always have enough to sell every week. While our remote sensing work is allowing us to do a better job of managing the crop that we do have, and potentially understanding where variation comes from and doing something about it, potentially with variable rate nitrogen application or other methods in the future. And in the end, we are not likely to see our total demand for the crops that we grow increase significantly. There's not likely to be many things that go on that massively grow the demand anywhere in the world really for lettuce products, the fresh produce that we grow. So in order to do what we do more efficiently, to provide continually better value to people, we need to be reducing the amount that we plant, getting more from less, really. So I will finish by talking about some other areas of interest for us. Obviously, you haven't seen any robotics here today because that's where you come in. We are very interested in mechanized and automated harvest as a way of helping us cope with labor shortage and upskilling our harvest teams in the future. We're interested in variable rate application of nitrogen and other inputs for that matter, rather than doing what the previous agricultural revolutions has allowed us to do, which is doing things efficiently at scale. We want to do things at scale, but also individually. which allows us to do targeted applications of pesticides, fungicides, any kind of chemical inputs to the field. If we're going to do that, let's do it in the most intelligent way possible. We're also interested in incorporating longer-term weather forecasts and sort of like stochastic-based supply and demand models to the way we manage our plans. We've got huge amounts of variability of sources of uncertainty in terms of what the demand every year is going to be or what the weather is going to be like. So there's quite a lot of modeling work that can go into just understanding that. And an area that I'm particularly interested in is digital twinning, is creating virtual versions of our fields that we can use to run scenarios, perhaps in that third theme there as well. Modeling the crop at a sort of population level as well as a plant level, and deriving some understanding from that. And of course, like everyone in agriculture, we're interested in early disease and pest detection so that we can spot problems as soon as they happen, before they happen, and do something about it. Again, minimizing the amount of inputs that we have to put into the system in order to deal with these kinds of problems. I'll just end with a slide that my colleague put together, talking about the 3 horizons model of innovation, of project management. You've got the first horizon, which is kind of sustaining innovation, projects that you've already invested in and now you're reaping the rewards from, and it's all about continuous improvement of those systems. And then you've got sort of second and third horizons of innovation, where it's more disruptive, where you're not seeing the benefit today necessarily, but you're investing for the future. The point that I like about the slide here is that this first horizon for us is our harvest process right now. We are, as you probably saw in the video, we've got mobile packing rigs that come into the field. We're basically cutting everything in the field and packing it into boxes and palletizing it in the field, so that all we have to do in our distribution center is cool the crop down to 4 degrees and then get it into cold chain and pass it on to our customers' depots. But that is the end of a very long story of innovation, starting with people hand harvesting in the 60s, moving on to some of the original infield packing, to what we call our auto wrapper systems, where we are basically putting plants onto a carousel where they're being wrapped and then packed all in field. And so there was decades of innovation that got us to that point. And if you told somebody in 1960s packing celery there in black and white that someday they'd be packing everything onto a conveyor belt in the field, I don't think they'd believe you. So when you post a video of a robot harvesting lettuce in the field and people say, oh, that's never going to work, they're not thinking about the right horizons. I think in 20, 30 years time, we're going to see that as we see our current harvest technology, how that looked 20 years ago. That's what we're going to see for this kind of technology, but we need to invest now in order to reap the rewards. And that is it from me. So thank you very much for letting me come speak to you today, and I will do my best to answer any of your questions. As I've hopefully tried to make it clear, I am not by any means an expert in any particular area, and we are a very large business. So if I can't answer your question, I will try to write it down. Feel free to email me, and I can certainly direct you to the right person in GES to answer any questions I can't cover today. So thank you again.
Okay, thank you very much, Iain. I think this is a brilliant introduction of a huge amount of operations happening in GES growers. So if you have any questions, you can speak up, or you can post it in the chat window. Then I can read out. Let me just start one basic question to Iain. I'm always impressed the amount of investment GES growers are putting in technology, innovations, and so on, which is not always the case with other growers and farmers. Do you actually have a good explanation why GES is so much investing into the future and technologies, and what's the difference, and how do you actually see the benefit for GES for investing so much on the future?
I think there's probably 2 differences between our company and maybe other people in the space. One is that we're family owned. So the kind of long-term perspective has always been kind of part of the business. I think it is, you know, I don't want to say that other businesses aren't thinking for the long term as well, but I think that's especially strong in our company. And the other is our scale. That 500 million pounds of turnover isn't big compared to, you know, Microsoft or Apple or someone like that, but in the farming world that is big. So the fact that we are a larger company, and I am particularly employed by a growers cooperative of 17 different growers across the UK, means that no one grower has to put up too much money. At one point, it's not too expensive for any one person. So really, it's collaboration kind of internally in our business that allows us to do that. And I think that's the story for the whole sector, is if we can be more collaborative, we will advance faster as an industry. The challenge then obviously is different firms not wanting to necessarily share their USP and their IP.
But that also depends on the track record, that how much you actually benefited from the previous investment, and I think you have so many successful stories so far.
Yeah, that we know that we have succeeded. Not everything we've done has been successful when you innovate like this, and sometimes you put money into projects and you don't see the benefit from those ones. But we've had enough benefits in the past to know that it's worth taking 5 years to try something like flying drones over your field and taking pictures when maybe other people aren't doing that yet, because that will give you the sort of first mover advantage. You'll know that technology may become available to other people in the future, and they may not have to spend as much money, but you will have spent those 4 or 5 years understanding how to use that technology. I think that's what we see. That's kind of why we're interested in these kind of investments.
Okay, thank you very much. Do you have any other question? Fulvio, do you want to go ahead? Yes.
Yeah, I'm impressed by the level of activity ESGs and the forward way of thinking. I mean, it's quite impressive. When I see your presentation, Iain, I see the modeling and sensing already quite developed, and the robotics, I see the example of FOMIA, which is one example. So somehow the robotics seems underdeveloped in comparison to the other one. So there is a fundamental reason for that. Is robotics particularly challenging? This is something that for us is very important in a certain sense.
Is it fundamentally challenging? I mean, is it difficult to apply it to our industry, like as opposed to others?
Yeah, in your direct experience, yes.
Well, I haven't had a huge amount of experience of applying robotics yet. I've been involved in the 2 projects that you've seen. But I think this sector does have some particular challenges. We're growing massive fields of green where it's difficult to see. You've got, as with anywhere in agriculture, you've got a really changing environment to deal with. So a lot of what robotics has learned in a controlled factory environment doesn't apply necessarily to the agricultural environment. So I think there's a huge amount of learning that needs to take place to apply technology, to apply robotics into the farm environment. And
the big machine that you have somehow are very effective for the current production, but do you think can be adapted, or we need a radical change? Because there are machinery, there is a heavy automation in the sector already, but somehow that doesn't seem to comply with the new needs.
Yeah, so we've automated, partially automated the packing process, but the harvesting process that you saw there is still very manual. You're harvesting a lettuce that's got a very short stem, and can grow into quite a surprising number of shapes, really. So it's a difficult one. We certainly haven't come up with a way of mechanically harvesting like that, like having a sort of saw blade cutting through the stems, like you saw perhaps with the spinach that's harvested mechanically. That's something we've not been able to necessarily crack with iceberg lettuce. So different crops are quite different. So there's different ways of going about it. One is adapting the way we grow to make robotics more successful in that environment. That's certainly one way we could look, and the other is relying really on your ingenuity to cope with the difficult environment. But yeah, the system we've got allows us to harvest very efficiently, as long as we've got a lot of very fit people working in the field, doing a very labor-intensive and difficult job. And that's becoming more of a challenge to attract people to the sector to do that. Certainly, if we want to keep food prices low. So. Yeah.
I just would like to let everyone know that I've promoted you as a panelist, so you are free to ask questions yourself if you want to.
But for me, I think you have your...
Emil, do you want to speak out your question, or shall I read it?
Hello, thanks, Fumia. Yes, thank you, Ian, for a very interesting talk. I have a question in terms of like the business point of view. What are the tasks that you think your business will benefit robotizing those tasks? So what are the like bottlenecks in your business that robots can help to improve and make a cost-effective solution to agriculture in your business?
Yeah, I think by and far harvesting is where we would see the biggest benefit. And that's one of the most costly operations for us to do. It's, as I just was saying, it's also one of the most difficult probably to crack, harvesting things like lettuces in a robotic way. Other ones include things like weeding, with some pesticides becoming restricted. Herbicides becoming restricted. We might need to go back to hand weeding if we can't come up with another solution to that problem. Again, it's requiring more labor and more costs that we can't really afford, and I didn't mention there. So solutions for weeding would be very important, and I think we've actually seen quite a lot of development in that area in the last few years. So I think solutions for robotic weeding are almost ready for deployment, really, and it's over the next 5 years, I'm sure we'll see some of that being trialed and deployed on our farms, although I don't know for sure. Other operations, I think it's those two probably are the biggest ones, I would say, weeding and harvest, if we can.
I see. May I follow up the question? Thank you. When you were talking about harvesting, is it just picking the crop, or is it involve any post-harvesting like packaging, or you're just referring to the action of picking only?
Well, as perhaps Fumia can attest to from Simon Birrell's PhD, in harvesting iceberg lettuce, there is an operation also peeling away layers and assessing when you stop and figuring out, okay, actually now I've got something that looks like what I would buy on the supermarket shelf. And that's an incredibly easy task for a human to learn. You can show somebody how to do it once and they know. Getting a robotic system to do that correctly, much harder, I think. That's just one step of the process. Then actually getting that onto, as you saw, our conveyor system and wrapping we've already automated that stage. And then getting those into boxes and palletizing them, there's kind of established systems of production to do those kinds of things. But it's the tasks that are really easy for humans and very difficult for robots that are the challenge. That's definitely, iceberg lettuce is probably one of the biggest challenges, for us.
Thank you very much. Cheers.
Sure. Thank you.
Okay, any other questions from audience? I actually have another question to you, if I may. So I like your spirit and ambition to really understand and control the crops, like vegetables, lettuce, and so on. What do you think is the limit of this? Obviously, these organisms are living, and there are lots of noise and lots of things out of control, or maybe just random factors, right? What do you think is the limit of all this controllability or identification? To what extent do we can identify the system in the end? How can we think about such a problem?
I think whatever solution we come up with will require us to be continually measuring the system. That we're never going to come up, well, perhaps someday we will come up with a complete mechanistic model for how the kind of crops we grow and the impact of different genetic varieties, have on that. You change this gene and therefore the stem grows, you see this expression and this change in the phenotype in the plants in the end. I don't think we're likely to fully describe the system of how these things grow, no matter how much data we get. So I think we're going to have to come up with systems that make approximations for that and then measure what happens, and then make corrections in whatever modeling work we do for what we're seeing happening on the ground. So I think the first step is collecting absolutely as much information as we possibly can. Every year that we don't do that is kind of wasted time. So it's not a task that we're currently doing necessarily, but if we could get, say, robotic systems to come and monitor our fields continuously, assess how big each plant is at different points in time, that data is going to be completely invaluable in understanding how our crops are growing, and then doing something about that in the future. But yeah, I don't know how close we ever will actually get to fully understanding and being able to predict exactly what happens if you know, if a particular weather scenario happens, what our lettuce is going to look like. I can't say for certain.
No, great. Yes, I think you know, we should be able to contribute a lot from sensing, timely sensing, and you know, large-scale sensing problems. And I think that's a really encouraging direction of research. Is there any other questions or comments from audience? If not, I think it's just 1 hour after from the beginning, so I think it's just time to close. So thank you very much once again, Iain, for a wonderful presentation. And as we know, GEES is a premier industry partner for our CDT project. So we're going to have lots of collaboration and discussions from now on, and we are very much looking forward to it. Thank you very much, Iain, once again, and we'll stay in touch.